Hello, and welcome to this video describing Einstein's postulates of special relativity. Einstein's postulates appear to be fairly simple on the surface, but they're actually quite involved and can lead to some mind-boggling scenarios such as time dilation and length contraction, which I'll briefly cover towards the end. This video will lay a foundation for understanding Einstein's postulates and what they mean in the world of physics. First, what is a postulate? Well, postulates are rules that can help explain and connect parts of a greater picture. Think about algebraic formulas that you've learned. On their own, they hold true. They also hold true when you're using multiple formulas to solve a bigger problem. That's essentially what we're doing with Einstein's postulates. We're using them to help understand more complex scenarios in physics. Einstein's first postulate says, the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. Einstein's second postulate says, the speed of light, c, is a constant, independent of the relative motion of the source. Let's take a closer look at this first postulate, which says the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. An inertial frame of reference is a frame in which a body at rest remains at rest, and a body in motion remains moving at a constant speed, meaning it doesn't accelerate. Let's look at an example to illustrate this. Imagine we're in an airplane moving at 500 miles per hour in the sky. You drop an object from your seat. What happens to it? Well, it falls straight down. What if you're in the same airplane as it's on the runway taking off? Since the motion is not uniform, you're undergoing acceleration, the object will not fall straight down. When the plane is moving at a constant speed in the sky, it can be defined as an inertial frame of reference. The physics laws that apply here seem to work exactly the same as when you're standing still on the Earth. Perhaps you have performed a similar experiment in a moving vehicle. You're driving down the road at a constant speed and drop something from your hand. To you, the object appears to fall straight down. To an outside observer standing still, the object would appear to follow a curved trajectory downward, as such. Along the same lines, imagine you're in the back of a limousine and the windows are all blacked out so that you can't see outside. You can't tell if the limo is sitting still or moving at a constant speed. Let's imagine you can't hear outside noises such as tires moving on the road. As we already established, dropping an object won't help you determine if you're moving or stationary. In either case, the object will appear to fall straight down relative to you. Say you are able to look out the window and you see your surroundings moving next to you. Could you definitively say that you are moving? Well, no. You could be moving, or your surroundings could also be moving and you might be stationary. Due to Einstein's first postulate, standard physics laws can't tell you if you are moving or if your surroundings are moving. We could say that an object's motion is relative to that of other objects in comparison, both of which must be inertial frames of reference. Let's take a closer look at the second postulate now, which says that the speed of light c is a constant, independent of the relative motion of the source. Let's look at a scenario when an object's speed isn't constant relative to the source. Say you're in a vehicle moving at a constant speed of 50 miles per hour. You throw an object forward out of the window at 5 miles per hour. An observer up ahead would see that object coming at 55 miles an hour, the speed of the vehicle plus the speed of the object. Now let's apply this to the speed of light. Say you're in a stationary vehicle and the headlights are turned on. That light is traveling at the speed of light, which is about 3 times 10 to the 8th meters per second, or 670 million meters per hour. Now, say the car is moving at a constant speed of 50 miles per hour. What is the speed of the light coming out of the headlight in this case? Is it the sum of the speed of light and the vehicle's speed, like in the example of us throwing an object out of the car window? Would it be 670 million miles per hour plus 50? Well, no. This is what Einstein's second postulate says, which was somewhat of a preposterous idea at the time. He said that the speed of light, c, is a constant, independent of the motion of the source. Say the car is moving in space at 99% of the speed of light. The light from the headlight is still faster than the car, moving forward 1% more. There's an observer on a distant planet. At what speed does the light arrive to them? You guessed it. The speed of light. 300 million meters per second, not 1.99 times the speed of light. The speed of light is a constant. Keep in mind that this postulate holds true in a vacuum or free space. We know that the speed of light can change as it passes through matter, such as glass or water. What are the implications of Einstein's second postulate? Well, according to the equation, velocity times time equals distance. When dealing with light, and speed is meant to change, but can't because Einstein's postulate says the speed of light is always constant, then that means one of the other variables changes. Time can change instead, leading to time dilation, or distance can change, leading to length contraction, which you can learn about in another video. So, to conclude, Einstein proposed two postulates of special relativity. First, uniform motion is relative, and the laws of physics are identical in all inertial frames of reference. Second, the speed of light c is a constant for all observers, independent of the motion of the source or observer.